Let's continue with this question 1vii using x2 of n equals to amplitude 1, but now the omega is now changed to 0.1 pi n, and we have a un here to say that this is a causal signal. So again, we are asked to find y2 of n for this x2 of n for this system. So again, the first thing we do is to use MATLAB to simulate. So x2 of n is this equation over here, and basically we use 50 samples of n, and omega is 0.1 pi. We then send this x2, which is a vector of 50 numbers. Using filter BA, we get y2, and we are plotting x2 as green and y2 as red. So let's see the figure now. The figure is this. Basically, the green is the cosine with amplitude 1, and the red is the output. Now, over here and here, this looks like it is the same, but in the front, it looks like it's not the same. So, in fact, the first few samples, the two samples are the transient conditions, and after that, it becomes a steady state. So, basically, you can think of the output as after a few samples it will be a steady state response, and because the input is a cosine, the output will be a cosine of the same frequency, but except that the amplitude will change as well as the phase. So it looks like the phase didn't change, but actually it changed a little bit. Okay, so we now know how to use simulation to get our output, and we see that there is a steady state response and some transient condition. So in our example, we want to find the steady state response. We are interested to find basically how big the signal became, because we now know that it is going to be a cosine and the amplitude is changing. So we now know that it goes from amplitude of 1 to about 4.14, and there's a phase shift. Okay, at least that's what the simulation tells us. So now let us see it using calculation. So again, to find the steady state response, all we need to do is to calculate h of ej omega, and now this omega is 0.1 pi, the frequency of interest, because we are going to send a cosine with a frequency of 0.1 pi radian per sample. All we need to do is to set z equals to 1 ej 0.1 pi, and then we substitute this value into h of z. So you realize that all we are doing is we are doing this. So z equals to, here is the plus, but because there's a minus, so minus appears here in these two equations. You must be very careful, and you should be able to do addition of the complex numbers, and then now out comes another complex numbers. So this is different from our previous example. Our previous example, out comes a real number, but you'll be surprised, right? You shouldn't be surprised, because we are sending z as a complex numbers into a polynomial or z minus 1. Out comes a complex number. It's a natural thing. Well, when we have it in rectangle form, it is not what we want. We want to convert into the polar form. So basically, this is the magnitude and this is the phase. So what we now can say is that our cosine, which is the original x of n, which is 1 cosine of 0.1 pi n, now is changed to this 1 is multiplied by the magnitude 4.14 cosine 0.1 pi n. So what we have is that we now know that our input cosine is modified by magnitude multiplied by 4.14, and its phase is plus, and then because here is minus, so we become we should actually write a minus now, minus 0.332 radian for the phase shift. Okay, so this is how you calculate the steady state response. So I repeat, to calculate the steady state response, you take h of z and you substitute z to be 1 ej in the particular omega that you're interested in, and the omega was 0.1 pi for our cosine, and we get a complex number. We convert it into the polar form of magnitude and phase, and we now use the magnitude to modify our original cosine's magnitude. This case was 1, so it's 1 times 4.14. Cosine, the same frequency remains 0.1 pi n, but since there's a phase shift of minus 0.332, we put it here. And this is our steady state response. Okay, so we have y1n and y2n. Of course, y3n is simply the sum of y1 and y2. Thank you.